Hi, this is Stephen, and in this video we will discuss how to quantify left ventricular function with echocardiography. And so let's look at the apical four-chamber view. So you have your left atrium that empties blood via the mitral valve into your left ventricle. Here's the muscular wall, and you have over here your right ventricle and your right atrium and tricuspid valve. And we are going to we want to measure the function of the ventricle. So we want to look at the ventricle now when it is at its largest, and that would be at end diastole, when it is done filling with blood. So I'm going to include an ECG down here. We have the P wave, atrial depolarization, QRS, ventricular depolarization, T, ventricular repolarization, P, and that would be right before the QRS starts to go up. This time here would be end diastole. Again, our QRS to T, this part is systole, and then our T wave right until the QRS starts, from the end of the T to right before the QRS starts, that would be our diastole. So this frame is right at the end of diastole when the ventricle chamber is at its largest, and I'm going to trace out inside so I get an area, something like this. Then I'm going to rotate my probe 60 degrees and get the apical two-chamber view. So that'll look something like this. Right when the valve leaflets are closing because we are at end diastole, the ventricle is just done. And let me actually shade in the left ventricular muscle for consistency with how we've drawn this so far. So LV, but from a slightly different angle at the end of diastole when it's done filling up with blood, and I'm going to trace out the inside over here in the apical two-chamber view as well. So I get another area. Now what I can do with these two areas is I can actually combine them to get a volume. And so the shape would look something like this. You have an arc here that comes from my apical four-chamber view, and then you have another arc over here that comes from my apical two-chamber view. And these can actually be taken together to form a shape. And you can use the Simpson biplane rule that's using calculus to find to sum up a series of disks and get a volume. Let's say that the calculated volume, the computer will calculate the volume for you. Let's say that was 100 milliliters. So that would be the end diastolic volume. By having two roughly orthogonal views, we can chart out the shape of this, the dimensions of this shape, and we can get a volume. Well, that's end diastole. What about at end systole when the chamber is at its smallest? So again, let's look at our apical four-chamber view. So the left atrium that empties blood via the mitral valve into the left ventricle. And now the muscular wall is much thicker because we're right at the end of systole. So this is the muscular left ventricular wall. And if we were to measure the volume here, the heart has pumped out most of the blood that was in it, right? So this area will be smaller. Let's rotate our probe 60 degrees and again measure. So this would be in our apical two-chamber, and you'll still have this thick left ventricle. Let's make that a little more symmetric, something like that. Thick left ventricle and a smaller cavity inside than we measured at end diastole. For consistency, let me draw the ECG down here. So QRS-T, we're going to stop right here because we are stopping right at the end of systole, right when the heart has pumped most of the blood, or as much of the blood as it can, out. And if I draw those arcs over here, this is what we get from our apical four-chamber view. And this would be what we get from our, something like that, is what we would get from our two-chamber view. Again, we're getting this solid shape that represents the ventricular cavity, and with some calculus, our computer can sum up a series of discs and get a volume. Let's say this volume was 30 milliliters. Well then, to calculate the ejection fraction, that's simply if you look at the large volume minus the small volume divided by the large volume, that's our ejection fraction. In our case, what would that be? Well, we said we had 100 ml minus 30 ml over 100 ml would be equal to an ejection fraction of 70% on the high normal side, or maybe a little hyperdynamic. So again, just to recap, we measure the area in two roughly orthogonal views at the end of when the heart is filling up with blood. We measure the smallest volume of the heart at the end of when the heart has pumped out much of the blood. We take the difference of those divided by the larger volume, and that gives us our ejection fraction, and that is how we like to quantify left ventricular function.